In this video, we will extend our Nyquist stability analysis by introducing two new functions called the sensitivity function and the complementary sensitivity function. To understand the sensitivity function and the complementary sensitivity function, consider this standard feedback control loop block diagram, where now, instead of the output being our controlled variable y, we're going to say our output is its measured value, y sub m. And the two inputs we'll call y sub d and y sub sp tilde, where y sub d is simply a disturbance multiplied by its transfer function gd for one input, and y sub sp tilde is the electronic signal representing our set point. We can compose y sub m as a function of y sub d and y sub sp using functions that look very similar to what we obtained for the regulator and servo transfer functions that we considered earlier. They're just formulated using slightly different inputs, and ym is the output instead of y as the output. The transfer function multiplying y sub d, that is, the response of y sub m to disturbances, we call the sensitivity function, s. And the transfer function multiplying y sub sp tilde, that is, the response of y sub m to set point changes, we call the complementary sensitivity function, t. The reason that t is called the complementary sensitivity function is because, as you can see here, the sum of s and t should equal 1. So t is the complement of s. This sensitivity function and complementary sensitivity function will provide us with quantitative measures of the process robustness, which up to this point we've only discussed in qualitative terms. Now, for ideal behavior that achieves perfect set point tracking and perfect disturbance rejection, we might want s to be equal to 0. That would mean that disturbances would have no effect on our measured value. And we might want t equal to 1, meaning that the measured value of our controlled variable would exactly track set point changes. Of course, process dynamics would prohibit this from being the case for a standard feedback control loop. Now, the sensitivity function is related to the distance between the Nyquist plot and the critical point on the Nyquist plot, which occurs at the point -1, 0 in the complex plane. The absolute value of the reciprocal of the sensitivity function is the absolute value of 1 plus GCG, or the absolute value of 1 plus GOL. If we plot this on the complex plane, it's very similar to the Nyquist plot, except that the origin has been shifted over to the point -1, 0 on the Nyquist plot, which was our critical point on the Nyquist plot. So instead of plotting the distance of the absolute value of GOL from the origin, we're plotting the distance of the absolute value of GOL from its critical point on the Nyquist plot. And the minimum in the absolute value of 1 over s is the minimum distance that the Nyquist plot makes from its critical point. And of course, that minimum corresponds to a maximum in the reciprocal, or a maximum in the absolute value of the sensitivity function. We call the maximum in the absolute value of the sensitivity function ms, and the maximum in the absolute value of the complementary sensitivity function mt. mt and ms are related to the gain margin by these relationships. ms over ms minus 1 is always less than or equal to the gain margin, and 1 plus 1 over mt is always less than or equal to the gain margin. These two maxima are also related to the phase margin by the relationships shown here. Therefore, large values of ms and mt make the process respond faster, but also reduce the process robustness. Some guidelines for feedback control loop design are that the maximum in the sensitivity function should be between 1.2 and 2, and the maximum in the complementary sensitivity function should be between 1 and 1.5 for well-tuned feedback control loops. The term sensitivity mathematically refers to the effect of one transfer function or variable on another transfer function or variable. For example, we could ask the question, how do changes in the process, G, affect the complementary sensitivity function, T, which you'll remember describes the response of the system to set point changes. The ratio of a fractional change in T to a fractional change in G can be obtained by taking these derivatives, and is given by 1 over 1 plus GGC, which is the sensitivity function. And that's why it's called the sensitivity function. The sensitivity function describes the sensitivity of the response of the process to set point changes to changes in G, or changes in the process. Now it turns out that feedback control reduces the process sensitivity. To understand this, consider the open loop process. The open loop process is one for which feedback control loop is disconnected at the comparator, so that when there's a set point change, that will result in a change in the measured value of the controlled variable, but will not feed that change back in to calculate the error signal. In this case, we might formulate an open loop complementary sensitivity function, TOL, which is just the product of G, C, GV, GP, and GM, or GC times G. The sensitivity of TOL to changes in G, or changes in the process transfer functions, is equal to 1. However, when we close the loop, the sensitivity, as we already showed, is equal to S, which is 1 over 1 plus GCG. Now, S, by this definition, must always be less than 1, and therefore closing the feedback control loop has reduced the sensitivity of the response to set point changes, described by T, to changes in the process, described by G. Now we can use the complementary sensitivity function to formally define robustness quantitatively. Suppose that there's some uncertainty in our model for a process, and we describe that uncertainty by the function of S, delta S, where delta S is the true behavior of the process described by G minus our model for the process, G tilde, divided by our model for the process, G tilde. The true behavior of the process is our model, G tilde, times 1 plus delta S, where delta S is some uncertainty that is a function of S. Now we don't know what that uncertainty is, but let's suppose it's bounded by some limit L, which could be a function of input frequency omega. In other words, the absolute value of delta of j omega is less than or equal to our limit of omega, where here that limit can be a function of the input frequency. Furthermore, suppose that the system composed of GCG tilde is stable, and that the number of right half-plane poles is independent of delta S, meaning that the process uncertainty does not introduce new instabilities or new right half-plane poles into G. Then we can say that the system is robustly stable for all values of delta S within our established limit if the absolute value of the complementary sensitivity function multiplied by that limit is less than 1 for all values of omega, where here we're using the complementary sensitivity function composed using our process model, G tilde, instead of G, which is unknown. The use of this formal definition for the robustness will allow us to tune feedback controllers to ensure that the control loop will be stable to changes in the process or to uncertainties in our process model that are within a bound that we can establish. Summarizing the content from Chapter 14 of the Seaborg text and Appendix J, the frequency response analysis describes the output of a transfer function when the input is a sinusoid and all of the decaying exponential terms have decayed. The Bode diagrams summarize the normalized amplitude ratio, or the amplitude ratio, and the phase angle phi as a function of the input frequency omega. We defined a critical frequency as a frequency at which the phase angle is equal to minus 180 degrees, and the gain crossover frequency as the frequency at which the amplitude ratio is equal to 1. Based on these definitions, we can establish the Bode stability criterion, which tells us that for an open loop transfer function with no right half-plane poles, and at most one critical frequency and one gain crossover frequency, the closed loop system is stable if and only if the amplitude ratio at the critical frequency is less than 1. This stability criterion is based on the open loop transfer function, and it can handle time delays without any approximation. For processes that have no critical frequency, they cannot be made unstable by changing the gain, which changes the amplitude ratio of the process. We also defined the gain and phase margins, which provide us quantitative measures of the relative stability. Then we developed the idea of the Nyquist plot, which contains similar information to the Bode diagram, but is a polar plot of the real and imaginary parts of the open loop transfer function. From the Nyquist plot, we can establish the Nyquist stability criterion, which is also based on the frequency response, but is less restrictive than the Bode stability criterion. The Nyquist stability criterion states that for an open loop transfer function with no unstable pole zero cancellations, the closed loop system is stable if and only if the number of poles to the right of the imaginary axis equals minus the number of times that the point -1, 0 is encircled in the clockwise direction in the Nyquist diagram. The Nyquist stability criterion has fewer restrictions than the Bode stability criterion. We also defined the sensitivity function and complementary sensitivity function, S and T, which provide us with measures of the sensitivity and the robustness of a process.